So I'm going to talk about the statistical application, and I hope you will excuse me that I will deviate a bit from Michel's work, because then it will be too boring for Michel if I talk about your own work. So it will be the statistics, okay? Let me explain the idea, how it will be organized. So I make this kind of flow diagram, and on the left-hand side you see statistics, and on the right-hand side you see probability and approximation theory. So I'll just go through this flow and jump to this part from time to time, because I need the tools there, and it goes like this. So if I give it a different color, you know we're going to start with that part. So we start with empirical risk minimization and maximal inequalities, and then we go on. So you will know all the time where we are. So this is the problem. You have some function, which I call R, and you want to minimize it. Okay, to find the minimum. And I call R a risk function. That's a terminology used in statistics, the negative terminology. And the problem is, so there's a certain risk going higher, but the problem is you don't really know the risk. So the risk function is an unknown function. So the problem is not computational, that you can be a very complicated function. How do you minimize it? I'm not going to talk about that. The problem is you don't know the function. So how can you minimize it? Well, by approximating it, right? So we know that the function is a function which is an average of some loss function. Here it is. This means average. So you have certain states, and you take the average over all these states. And the average is with respect to some distribution, which I call P. And L is here a given loss function, and P is unknown probability measure. So you don't know the probability measure. So just to give you an example, so we know that getting married is a very difficult problem. So let me just look at that problem to start with the most difficult case, okay? So X is, so you consider marrying, and X is the persons you might want to marry. You just look, okay, you're a very rational person. And the possible states of the world, so how things will develop in future, is not known. But why is the possible states of the world? And given a possible state of the world, you have a certain loss when marrying person X. I'm sorry, this is a negative way to put it. So you call it a loss function, but maybe I should call it a happiness function, or minus happiness. Call it minus happiness. Okay? And the states of the world, the distribution of the states of the world is unknown. So you don't know what the future will look like, how things will develop. And the risk is just the average loss when you marry person X. So it's the average gain and average happiness when you marry a certain person. Yes, and then you want to be as happy as possible, so you marry the person with who you think you'll be the most happy with. So that's the problem. So we don't know the future, so we replace it by some estimate. So the unknown probability measure is this red P, and I replace it by a known probability measure Q, the blue one. So the average with respect to this known probability measure is depending on that measure. So I put a subscript here. And so the risk depends on how you average the loss function. And then instead of taking the minimum of this unknown risk function, which is, I call it a theoretical one. In theory, it's somewhere, but you don't know it. It's a theoretical risk. And I minimize instead of that one, because I can't, I don't know it. I have here a known risk function, which I call the empirical one, because I know it. I minimize that one instead. And the question is then, how good is that estimate? Okay? Well, you just look at what would be the optimal risk. So that's the risk in the minimum. So here's the minimum. Here's the unknown, so the theoretical risk, the red one. You minimize it, and then you get a certain happiness. Well, minus happiness here. Okay. But instead, you have some idea about the probability measure. You use that one instead. So that's the blue one. You minimize it. And then what is the loss? So what happens? You have a certain excess risk, which you can think of a measure of disappointment when marrying that person. That one instead of that one, so this one would be good, but that way you married the wrong person, so you have a measure of disappointment. I call that the excess risk. Okay, and that is something you want to bound. Eh? You want to bound your excess risk, your disappointment measure. Okay, so excess risk is a quantity of interest. Okay? And that's where this inequality comes in. The excess risk can always be bound by what I call the empirical process. The terminology is a bit strange here. But there is a bound here, what I call the basic inequality. This is a very straightforward bound. It's just a couple of lines, but of course I'm not going to write it down because but you believe me, it's really very simple, two manipulations of inequalities. Okay, so if you believe this to be true, then the message is now, if you want to bound this disappointment measure, well, one way to do it is to bound this empirical process. Okay. Now, how do you, there's an unknown probability measure. How do you approximate it? Well, you approximate it by looking at the data, so looking around what would be the development of the possible states of the world. You sort of estimate the unknown probability measure by looking around at data. And as a statistician, I think data are random. That means they are fluctuating. If you ask this person about the future and another person, they will give different answers. So it's something not very certain, okay? So you have your data which are random, and that means if you base your probability measure on random data, it is a random probability measure, okay? And typically what we do in statistics is then put a hat on. So something with a hat on is random, but observable. So it's an observable random thing. Here, a random probability measure. Now, if you look at then the risk, where instead of the true probability measure, you put this estimate, which is random, you get a random function, okay? And if you look at the excess risk, this disappointment measure is then a random thing. So I put a hat on it. So, now we come, as Michel also explained, so the risk function is a function with a certain domain, which I'd say the argument is X, sort of giving the idea that it's a real valued, the domain is the real line. But if you think about marrying a person is not a one-dimensional object, right? It's more like an abstract thing. So okay. So instead of X, to sort of remember that it's something abstract, I call it F. F is like, maybe a function, maybe a vector or an infinite dimensional vector, and then I call it a function. But just to say that it's something more abstract than just a real number. That's to stress that. So what Michel called T before was now, in my case, F. A function. Let's say a function in the space of functions, which is script F. So the risk is a function on the space of functions. Okay? And I just put the dependence on the arguments in a subscript. So this is just change of notation. Sorry for that, but it may be helpful to understand that, yeah, actually, we're not on the real line. So, okay. So everything is the same. So the empirical risk is the average of the loss at the function f. The theoretical risk is here. And the minimizer, I call that the target or whatever, so I call that f0, the minimizer of the theoretical risk. And the minimizer of the empirical risk, f hat, so that's with a hat because it's random. And the excess risk, the measure of disappointment is now just change of notation like this. And then the basic inequality looks like this. And now if you have here an empirical measure and the true one, this is called the empirical process. And it's not a process, but because there is it's a random variable, but because there is a random evaluation here, so it's a function of a random function, it means that if you want to bound it, it may be helpful to bound it uniformly over a set. And because if it would be hold uniformly, if something holds uniformly over a certain argument, it will also hold for the random variable, okay? So that's why uniform bounds are useful in statistics, so maximal inequalities. I'm sort of formulating it like this. Suppose you want to prove that the excess risk is bounded by something small, like delta, some small quantity. Then what you can show, if you have a function for which the excess risk is bigger than delta, then this will not hold. And hence, your excess risk will be less than delta. Okay? So you need some kind of for all thing here, or you don't need it, but it's helpful. So it means you want it, in fact, to be uniform because this probability should be true for all, not, okay, for all f with large, okay, I first put for all and then the probability outside. So you need some uniform results. And that's maximal inequality, so there's a supreme, so you just look at the empirical process. It's now a process in terms of it's a process depending on f. And then you take the supremum over some set which is convenient for your problem. So you take the supremum or the maximum if it's a finite set, it's just maximum. So this opens up a lot of applications, and what we need from probability theory and so on is what the tools we use is symmetrization, the contraction theorem, and concentration of measure, and then generic chaining. So I'll just look at that last part, generic chaining. But to do that, okay, here's what I'm using all the time in my life. So these are the books which are permanently on my desk. Generic Chaining from Michel Talagrand and Probability in Banach Spaces from Michel Ledoux and Michel Talagrand. And that's what I use. So I won't go through all the technical details, but I'll just try to give you a glimpse. Of course, this marrying thing is just not a serious example. So in statistics, there are loss functions all over the place, and maybe you know the least squares method, least quadratic loss. If you do least squares, maximum likelihood, that is a minus log function, loss function. Generalized linear models support vector machines and whatever kind of loss functions you use for classification and so on. So once you have a loss function, you have a risk function, and you minimize it. But, so everything I'm going to say next is for least squares holds for also for the other models, but it gets, of course, more complicated. So saying, okay, let's look at the simplest case containing all the ingredients also to make it extendable to the more complicated case, but just simple case so that you see what's the main point, okay? So now we're here. So I hope you more or less see what I meant by maximal inequalities. And then as a special case, I'm going to look at the regression model. So we're not yet here. Regression. So what's regression? Maybe I'll go to the next slide here. That's maybe better. So regression is that you have an input x and an output y, and then there's noise. So the output is determined by the input and the noise. And saying that the output y is a function of the input x plus noise, additive noise. And this function is unknown, but we know it's going to be in some model class script f. Okay? That's regression. So y is the vector of observations, and the number of observations is n. F0 is an unknown regression function, and we evaluate it at the design points, so you can think of it as a vector. It's in some space of regression functions, and psi is the vector of noise. Okay, so the model is y is f0 plus psi. Here it is. So you have a known space of regression functions. The true regression function is somewhere in there. That's this f0. Then there's this noise, and what you observe is the vector y. Huh? And then you want to recover f0. You want to recover this function, the regression function. Okay. So here it's again, suppose the input is one-dimensional, and so the output is the vector y. That's what you observe at each input point. And then you can think of a linear regression, where you try to fit a line through your points, or monotone regression or isotonic regression, where the only requirement you have when you fit is that the function should be monotone. Or it could be that you require the function to be convex, or you require the function to be of bounded variation. I'm not going to explain in too much detail, but you can you have functions in higher dimensional spaces, and then assume bounded variation in higher dimensions, which is sometimes useful for image analysis, or some smoothness, or maybe other shape restrictions. Smoothness is typically that you assume that the function is a certain number of times differentiable. And if you want to be fancy, you mention neural networks. Okay, it could also be a one hidden layer neural network. Whatever you are thinking would be a good model for your regression function. So there's this space. That's the model for your regression function. That's this script f. And then your estimator is using the quadratic loss. And then you get the least squares estimator, which just uses the point in your model class which is closest to your observation. And that's my estimator f hat. So that's indeed a case where there is a loss function defined, which the loss function is now just the distance between y and the function f. So that's the Euclidean distance. And then you have the basic inequality. So remember, you have this basic inequality always. And in this particular case, it's like this. The excess risk, so this disappointment measure is just the squared distance. And the empirical process is this inner product. Inner product of a function with the noise. So now we're exactly in... So if we want to bound this, we only have to bound... It's okay to bound this term. And we're exactly in this situation that Michel Talagrand described. You have an inner product of something fixed times a Gaussian vector, because I'm going to assume the noise is Gaussian. Okay, so you have here differences, f hat minus f0, but you can just forget about the differences because of means being 0. So what you end up is studying inner products of a vector with a Gaussian, with psi, with the noise. So we would be helpful for our statistical regression problem to have a maximal inequality for this supremum of this Gaussian vector. And then we have bounds for the estimation error. So that's good. So to get a sharp or tight bound for this empirical process, we know now that we can use chaining, and in particular for the tightness, sharp bounds, generic chaining. And I just will give you my simple naive version. I don't know, because I didn't know that it would be explained in good detail. So I'm going now to the right side and do some probability theory, or actually generic chaining there's hardly any probability involved. It's just approximations argument. And this is my version. So like Michel, I'm going to say, okay, let's just assume that the class of regression functions in our case, let's just assume it's finite. It can be huge, but finite. If it's not, you can always have a little approximation term to make it finite. So let's suppose it's finite. And I call it GS, and that's G stands for generation number S. That's the last generation. This is my class of regression function. All these nodes represent a point in my class, which I start with. And I then build a chain, a tree in my case, from the last generation to the root. G of S is some point in the last generation. G of S minus 1 is the parent of this guy. And you continue, so you have children with parents, and the overall parent of everybody is G0. So you build this kind of tree. So these are the generations, G0, G1, and so on. And each child has a parent in the previous generation. And if you look at the length of a path from somebody in the final generation to the root, it's just the sum of the length of the path from child to parent. That's what this says, okay? And then the maximal path length I call sigma. So that's the chain, going from the child in the last generation all the way through the tree to the parent. That's the chain. Okay. And then the gamma functional, gamma 2, is the sum of the length of such a branch times the square root of the logarithm of the number of elements in generation number S. That's the gamma functional, and then there's a little S log 2, which is in green because it's an uninteresting constant, giving an uninteresting constant. And then the expected value of this maximal, so this empirical process, the maximal of this inner product, is bounded by gamma plus sigma square root of 2. Okay, so that sort of solves the regression problem. Oh yeah, I have this one, if people worry. So this is just, where is it? This is just a bound for the expectation. You can also write down some kind of exponential moment, and then you get concentration of measure. So it's enough to have the expectation, and then the probability that it's far away from the expectation is going to be small. Yeah. Also, I hope this is more or less not too much simplified version. Okay. But as Michel said, it is very difficult extremely difficult in many cases to really compute the gamma functional. So let's look at two simple cases. And before doing that, I'm going to recall Cauchy-Schwarz and more generally the dual norm inequality. What does Cauchy-Schwarz say? Well, the inner product between two vectors can be bounded by the product of their lengths. That's because if you have two vectors, the cosine of the angle between them is the inner product divided by the length, and the cosine in absolute value is always bounded by 1. Okay, so that's Cauchy-Schwarz, right? You're with me? And more generally, if you take the inner product, you can bound it by the L1 norm, it's called, and the L infinity norm of the vector. The L1 norm is the sum of the absolute value of the coefficients, and the L infinity norm is the maximal value of the coefficients. Okay, so this is the dual norm inequality. Actually, these are two special cases, but let me refer to this one as Cauchy-Schwarz, and that one to the dual norm inequality. And I forgot what to say. Okay, so I'm going to use them now for bounding the empirical process. So let's think of first doing regression, linear regression. So then the input matrix is a matrix with the number of variables p and the number of observations n. It's a matrix consisting of p columns. P is the number of variables, and each column is a vector of length n. So I'm now going to take linear combinations of those columns with coefficients beta. So here it is. So you have, say, p equal 2. You have two vectors. You give them coefficients beta 1 and beta 2, and then you take the sum, and that's then x beta. Okay? And the linear model says that my regression function is such a linear function, where beta, the coefficients, are the unknown, unknown parameters. And then you can prove that the excess risk on average, remember it's a random variable, but on average it can be bounded by the number of variables divided by the number of observations. And why is that? Well, you can of course use the chaining argument, and you can also just use Cauchy-Schwarz. Actually, it's very easy to prove that the chaining argument gives you exactly the same thing as Cauchy-Schwarz. And Cauchy-Schwarz gives you this. So you apply Cauchy-Schwarz, the basic inequality, which I showed you, and then you get this result. So what does this say you? It tells you that the more observations, the better, and you shouldn't have too many variables, because then this will not be small. Okay? So the design, which is a n times p matrix, the number of variables should be small as compared to the number of observations, so that this is small. So the matrix is standing on its side, which is small. Okay. Okay, that's. I'm going to move on to another special case, a convex class of regression functions, because, well, not for a particular reason, just because there I can use this other dual norm inequality and see what happens. So that's going to be the case in the rest of the talk. So the class of regression functions is going to be, again, the linear one, but now with this restriction that the L1 norm is bounded by 1. The L1 norm is the sum of the absolute value of the coefficients. So it means I have my design matrix, and it has p columns, which I can make a picture of that. So these are vectors. And then I take the convex hull. Maybe I also take their negative values. Take the convex hull. And that's my class of regression functions. And then the excess risk on average is bounded by square root 2 log p over n. And that's again, well, you can use the generic chaining bound here, but you can also just use this dual norm inequality and the basic inequality, and then you get this. I'm not giving all the details, it's just very simple. So if you look at this, the number of variables occurs logarithmically. So that can be much larger than the number of observations. So the number of variables can be large. But the number of observations, the bound in terms of the number of observations has this square root. So instead of 1 over n, you have 1 over square root of n. So that's worse. Okay. So this is a tight bound if the XJs are almost orthogonal, and the same bound is given by generic chaining. And if you apply Dudley's entropy integral, you get additional log terms which are superfluous. So what you do here, so this is kind of what you do if you are a good runner. You can start chasing log terms, and generic chaining really catches up the log terms here, right? I hope. So, so what if you have this convex class of regression functions, but the functions are highly correlated, maybe like this? Let's see. So then we do this. So we now go to approximation theory. We go to the right again. I'm going to look at approximation numbers. You can say, okay, let's just do generic chaining, but I'm a statistician, but even a naive one, thinking about how can I bound this? Okay, you just try something without trying to look at all these difficult probabilistic arguments. So this is going to be a naive bound. And it's based on combining Cauchy-Schwarz and the dual norm inequality and nothing more. So how does it go? I have to define approximation numbers. Well, let's first think of approximating by linear spaces. So here V is a linear space. And the distance of a vector to a linear space is just this. So you project on the space, and then this is the distance. Now we have our design matrix consisting of several vectors. And for a linear space, I look at the maximal distance of each column to that linear space. And that is then called the distance of X to the linear space V. And then I take, for a given dimension, the linear space with dimension, well, given dimension n. I look at, among all linear spaces with dimension n, I look at the one which has the smallest distance to X. Well, that's one thing. If you don't understand it, doesn't matter. It's just, I have to say something, otherwise it doesn't. Yeah, you have to define it, but it's about the idea. And the idea is that you have to look at this number. This is the smallest dimension, such that the distance of a linear space with that dimension to the design is at most epsilon. So for each epsilon, you can define the following. The epsilon approximation number, it's the minimal dimension n. You need that the distance of the design to the linear space with dimension n is most epsilon. Okay. Then, if this approximation number so you can define it for all epsilon, and as a function of epsilon, if it behaves polynomially in epsilon with exponent w, then the excess risk on average can be bounded by something polynomial in 1 over the number of observations, and the coefficients are like this, 2 plus w over 2 plus w. So the point here is that the smaller w, the better off you are. And so this is telling you how much better am I doing if I have more observations, and how much faster does this go to 0 if my w is very small. Okay? And here are the log terms, which are in green, because for the moment I'm not going to chase the log terms. I'll do that later on. It's really very difficult. It's all in the logs. I know that the theory is difficult because it's all in the logs, and I'm not... Yeah, I want to give you just the main terms, say, which are these ones. And this is really not much more. To prove this is much more than Cauchy-Schwarz and the dual norm inequality, and then this basic inequality. It's combining 3 simple things. Okay. So now that's the approximation numbers. Let's look at some examples. Now, I have to say, maybe at this point, that if I move on, it gets more and more incomprehensible, okay? But I don't want to give... It's difficult. You don't want to give the impression that I only do stupid things, so I want to impress you somehow. Okay. But let's first look at examples. Here. Maybe look at the next slide. Here. Suppose you want to estimate a monotone function. Huh? Okay, now I go back. So a monotone function, you just think of a monotone function. Well, a distribution function is monotone, right? We know this. Distribution function is monotone, and it's bounded by 1. And you can think of it as being a mixture of Heaviside functions, which are these degenerate distribution functions. The Heaviside function is 0, and then jumps to 1 at a certain point. So if you put them as the columns of your design matrix, it's just constant 1, and then it's 0, and then constant 1, 0, constant 1. So this is your design matrix. And if you then take the convex hull, you get monotone functions. And if you take the absolute convex hull, you get functions of bounded variation. So this is an interesting class of regression functions. And what are the approximation numbers? Here's the Heaviside function, the black one. Here's the real line. You make a little grid of size epsilon squared here. And then the red function and the black function, they differ only on this little area here, which has size epsilon squared. And then I'm saying quickly, the L2 norm of a function is the square root of an indicator is the square root of its L1. Okay, so that's why you need epsilon squared, not epsilon. Just believe me. So W, the exponent, the approximation number has exponent 2. Then you put that in the general statistics theorem that I showed, and you get the rate of convergence with exponent 2/3. And the log terms we still have to chase. You can extend that to hinge functions, or more generally, truncated power bases. So the Heaviside function is 0 and then jumps to 1. Hinge function is 0 and then linear. And this one is 0 and then quadratic. So that Heaviside corresponds to Q equal to 1. You can think of Q as sort of as the number of derivatives in a certain sense. And so the exponent in the approximation number is like this, depending on Q, the power you're taking. And so the rate of convergence is like this, 2q over 2q plus 1. So you can think of it, for instance, if you take the hinge functions, if you take convex combinations of hinge functions, you get something like monotone convex functions. Or maybe you have monotone pieces, so convex functions have q equal to 2, and you put the 2 here in, you get 4 over 5. So the rate of convergence is n to the power of 4 over 5 in a log term. So that's quite much quicker than if you only assume monotonicity. Kronecker products. Suppose your design is the product of functions. I'll go very quickly here, just because of the view of time. And then you take the convex hull. So you can think of here as the number of, you take sums of products of functions, and the number of terms in such a product is d, that's the dimension. Now let me skip this, not to confuse it. And if you assume that the approximation number with one dimension equal to 1 is polynomially in epsilon with exponent w, then in d dimensions it's still polynomial with exponent w, the same w, and the dimension now only occurs in the log terms. Okay, so it's high time that we start chasing log terms because they start becoming interesting. Okay, but the important thing is that it doesn't matter, just to be sure. So if you have dimension 1 or 2, for Heaviside functions the exponent is still w, but there is a log term, and so on. So the exponent, the main term doesn't change, only the log term changes if you go to higher dimensions. So if you do products of Heaviside functions, so if you take the product of the indicator of a half interval in one dimension, if you take product of those in 2 dimensions, you get half intervals in 2 dimensions. Huh? So that's a special case. And in general, with Heaviside functions, and you take products, you get half intervals in d dimensions. And we saw before that for Heaviside functions, the exponent is 2, w is 2. And for in higher dimensions, it's still 2. And then you get a log term depending on the dimension. So you see, if you do least squares, so for Heaviside functions, you can think of taking the convex hull. So that means you take the class of all distribution functions in higher dimensions. And if you do that, if you think your regression function looks like a distribution function, the rate of convergence, no matter what the dimension, is 2/3, and there's a depending on the dimension in the log term. Yeah. Now let's just that's based on the Haar basis or other wavelet arguments. So let's just quickly now go to entropy and small balls. This is the part I'm trying to be more incomprehensible, even more. So, like Michel said, we have a metric space. It was called T in his talk and in mine also. You have a metric space with a metric on it or a distance. Then we can describe the richness of the space by the entropy. So what is it? Take an arbitrary epsilon and try to cover the space by balls with radius epsilon. These little cucumber disks. And the number you need is called the epsilon covering number, and the logarithm is called the entropy. Okay, so that's a measure of the complexity of the space. And it's well known that if you want to have maximal inequalities, you want to bound the right-hand side, and you don't want to use the generic chaining, you can use Dudley's entropy integral. So entropy plays a crucial role for maximal inequalities. So how does it relate to our result? It says that if you know the approximation number, with exponent W, then the entropy of the convex hull has exponent 2W over 2 plus W. And in green are the log terms, and we're going to change them a little bit. Okay. So from approximation numbers, you get entropy bounds. So you end up in approximation theory here. This has nothing to do with statistics, but it's, as a statistician, this is what you encounter. You have to think, can I apply this? So as a special case, if you have the approximation number for the one-dimensional case with exponent W, you also have it for the d-dimensional case with exponent W and some log terms. And then if you take the convex hull, you get a bound for the entropy of this complicated class, where the exponent is like for the one-dimensional case, and the dimension is in the log terms. Maybe to go a bit quicker, let me just quickly. So, of course, the question is, the question is there, does the inequality go both ways? So the bound for the entropy and the bound for the approximation number, are they so tightly related? So is it if and only if? And I'm not going to answer this question. It's more or less if and only if. I'm still a little bit, I think it is, but I'm a little bit suspicious. But at least it's, the bounds we get is, at least in certain cases, sharp or tight, even up to log terms. So this is really going really fast now. But we'll end up again with results by Michel Talagrand. Small balls. So I asked the question, I have all these bounds, are they tight, are they sharp? And then I got into problems, because then I have to go into this convex geometry type of results. Pissier, I guess, is the main reference here. So so you can think of, I have L1 norms, L infinity norms. You can think of Banach spaces and Hilbert spaces. There's the duality theorem. So just to tell you, I got really stuck. Packing numbers, volume. What is all this? But so just this thing, packing number. So what I talked about entropy, and related and more or less the same is the packing number, same as the covering number. Packing number of a space, in this case this box, is the number of balls that fit in the box. The number of balls with radius epsilon. That's the packing number. And small ball estimates has to do with, well, if you're going to pack balls in a box, you better know how large they are, so you estimate how large these small balls are. Okay. And then the small ball estimate is this quantity. Here's the small ball for the baby. So you go to something like a joule. Maybe people who know this, they like to see it, but otherwise don't worry. You go to some kind of joule norm, and then you measure the size of a Gaussian vector in terms of this joule norm, and take minus the logarithm because it will be exponential type of behavior. And what I think, so there's a strong connection between small ball estimates and entropy, right? Then quickly, if I did it correctly, the small ball estimate can be bounded by the approximation number and a log term. And then, so I'm not going to be, because this is recorded, I think, right? So maybe I say things wrong, but at least in this case, for the half intervals in d dimensions, so think of higher dimensional distribution functions, I have this estimate for the approximation number, and hence I have an estimate for the small ball. And it turns out if we look at the paper by Talagrand, Michel Talagrand, that this is for d equals 2, it's tight, it's sharp. So somehow we were very naive, but somehow it seems that we did change the log terms in a certain sense. So it all goes back to even Bas, 88, small ball estimate for the Brownian sheet, and then Michel proved that this estimate is tight. You see the exponent w equal to 2, the log terms, and this is the bound for general dimensions, which is certainly not tight for d equals to 1. But this is where I ended up with when first starting, for some reason, doing just this Cauchy-Schwarz and dual norm inequality, and then I suddenly end up in this kind of theory. This is what happens if you're a statistician. So let me summarize. These maximal inequalities play an important role. Generic chaining gives sharp bounds. They are very difficult to compute, and that's why statisticians sometimes use simple naive bounds. And they sometimes even happen to be sharp, but not always. And also why I like statistics so much, in fact, is because it uses a lot or almost everything from mathematics, such as probability theory, approximation theory, convex geometry, and so on. Okay, I think that's it. I want to thank you very much for your attention.